In this video, we're going to discuss two sample t-intervals. Two sample t-intervals are one method of comparing characteristics of two populations. Unlike matched pairs, there is no matching of units, and the two samples can be different sizes. As we see, the conditions and assumptions for our full inference toolbox are pretty basic. We have to assume that, are we taking two simple random samples from two distinct populations? If we are, there is no overlap, and hence the samples should be independent from one another, meaning one sample has no influence on the other. Is the sample normal enough? Do we have a large enough size sample to consider the distribution normal and symmetrical? Or is there some sort of statement in the original question that can sort of allude to the fact that we're drawing from a normal population or make that assumption? And then lastly, is the sample size for each sample less than 10% of its respective population? If it is, we can proceed to use a two-sample t-interval. As we begin to work with an actual question, we want to make sure that we discuss in context the population of interest and the parameter of interest, and again, making sure that we discuss this in context. We know from experience that we're going to need a standard error in the creation of this confidence interval. Now, if you remember back to random variables, we discussed the fact that you cannot add standard deviation. So what are we going to do? We're going to take our sample standard deviations and we're going to change them into sample variance, because we can add variance. And it doesn't matter whether or not we're taking the difference or sums. Remember, we always add variance. So in our confidence interval, even though we're going to look for the difference between the two samples, we're still talking about the sum of the standard deviations or the sample variance. And in our sampling distribution conversion, we're going to take our variance of sample 1 divided by the size of sample 1 and our variance of sample 2 divided by the size of sample 2. So let's take a look at what the whole confidence interval looks like in its raw form. So as you can see here, it's of no surprise. You have your sample mean from population number 1 minus our sample mean from population or sample number 2, plus or minus our critical value of t for n minus 1 degrees of freedom. And it should be noted that the n minus 1 degrees of freedom is for the sample that's smaller, or I should say the smaller sample. So if you have a sample of, say, 52 and you have a sample of, say, 47, then your degrees of freedom is going to be equal to 47 minus 1, or 46. So we go with the sample, that's the smaller size, times your standard error. All right, let's give one a shot. Take a minute and press pause now and just read the paragraph that we have here so I don't have to read it for you. On a side note, if it's blurry, try to restart the video. It might just be a slight buffering issue. Press pause now. Okay, so what we're talking about is angular velocity of the knee for both skilled female rowers and novice female rowers. One of the things that they offered us was that the data show no outliers and no strong skewness. So that justifies our normality piece. But let's start fresh. First, we'll identify our population. The way I see it, it's competitive female rowers, both skilled and novice. And the parameter that we're discussing about them is the true mean difference in angular velocity between them. And I'm going to be honest up front, not exactly sure what kind of units we're using here. We'll just use the word units. As we go through our assumptions and conditions, the first one is on the list, is this a simple random sample? And so we're going to have to assume that this is a reasonable set of two different simple random samples. Is it normal enough? Well, as I said just a moment ago, it said that the data showed no outliers or strong skewness. So we're going to say yes, good enough for us in AP statistics. In real life, I think we'd probably like to take a look at the data a little bit more. And lastly, I think it's safe to say I think it's safe to say that I forgot to give you the most important information, the summary statistics. There we are. That's better. As we see, our sample size for skilled women rowers is 10, and the sample size for the novice is 8. So now I can say, I think it's safe to say that both of those are less than 10% of the respective populations. Therefore, I think it's okay that we proceed and use a two-sample T interval. And we will proceed with that now. The course of action we want to take now is to construct a 90% confidence interval for the difference between skilled and novice female rowers. You have all of your summary statistics here. Using your T table, decide on the appropriate critical value of T and substitute in all the other information necessary to complete the interval. Then actually calculate the interval by hand. Press pause, do all of that now, and then I'll substitute in my work and we can compare answers. All right, well, how'd you do? First, please sort of disregard my little faux pas over here. I had left some exponents in there by accident for the sample sizes. But anyway, here's our difference of means, 1.895. That is the critical value of T associated with degrees of freedom equal to 7 here. The reason that we're choosing 7 is our smaller sample is size 8, and n minus 1 would be equal to 7. So as you follow the chart for 90 degrees, 90% confidence up to the row that's associated with 7 degrees of freedom, you see a critical value of T of 1.895. When you use technology, it follows a more critical calculation, which becomes a little bit more precise. And so when we use the calculator to check our answer, we're going to get a different answer. And we just want to be aware of that fact. And that is because of the difference in the calculation of the critical value of T. Nonetheless, this is the minimum amount of work that I would expect to see on your paper. Substituted all the values in. We have the raw formula sitting here. We have our difference in the sample means, plus or minus our margin of error, and then a final hand-calculated version of our interval. Now we need to interpret it. So here we are. We are 90% confident that the true mean difference in angular velocity for skilled and novice competitive female rowers is somewhere between 0.4691 and 1.8765 units. I tried to dig around on the internet, and it looks like the unit should be radians per second. I put a question mark because I may be wrong, and I don't want to dwell on just the units. So I think we have a pretty good handle on what's going on here. Let's take a look at what it looks like on the calculator. First, we want to go to Stat, Test, two-sample T interval, choice 0, which brings us to our two-sample T interval. We choose statistics because that's what we have, summary statistics. Otherwise, we would enter our data into lists and choose data. We've put in our sample mean, our sample standard deviation, sample size, all for sample 1 and respectively for sample 2. Put in our confidence level, and now here's a new one, pooled. Essentially, we're pretty much going to check no here. The only reason we would say yes is if we thought that the variability in both samples was the same, or that sigma was the same in both samples, or that the variance is the same. And we're drawing from two different populations, and we're assuming that they're different and independent of each other, it's almost silly to choose the answer yes. So let's just say, as a rule of thumb, we're just going to answer no all the time here. Two sample t-interval readout here. Here's our 0.49817 to 1.8474. Like I said, it's slightly different than our 4691 and 1.8765, and that's because of a slight difference in the way that the calculator calculates the t, or the critical value of t. If you'd like to read more up on that, it's on page 659 of your textbook. That about wraps it up for two sample t intervals. Hopefully this was helpful.